Okay, thank you for inviting us to share our experiences with you. I feel like the bad guy in the room. You're all here kind of shifting the bits across the network, and we're the people that are actually putting the bits into the network with video. So yes, I'm Nigel Harniman. I'm a solutions architect for Brightcove in the EMEA region. And yeah, we're going to talk about how we can potentially reduce the amount of data that we need to shift to deliver high quality video. So what I'm going to cover off here is we're going to look a little bit at history of video over the last couple of decades and how the data rates have grown. We're going to look at the challenges of scaling the network. You're probably well versed in that than I am, but I'm going to put our perspective on that. And then we'll get into the nuts of this, which is how we think we can apply machine learning to actually improve the compression and actually get more out of the current technologies. And then right at the end, I'll give us some insights into where else we're seeing machine learning being kind of applied in the video space. So who remembers this type of video experience? This is actually from the BBC website, the news website, back around the year 2000. Everyone remember the sort of when video looked like this? It was a real audio stream or real video, and you had a 28 kilobits per second video option. Everyone remember that? What's happened in the last nearly 20 years? Well, we've gone from small resolution images through the different resolutions up to probably HD today we're fairly comfortable with over the top. And we're seeing services now pushing kind of 4K. And as you will know, the kind of what's happened on the network is the bandwidths have gone from the 28K dial-ups. We all remember the US robotic Sportster and its noises as it used to dial up. And now we're kind of looking at 40 megabits is a fairly standard fibre to the cabinet option that a large number of people in the UK have access to, and then some are even luckier. They've got probably cables or fibre into the building, and they're getting over 200 megabits per second. So what's actually happened as we've done that is we've allowed the resolutions to increase as the data rates through the network have increased. Which has come first? I don't know. We've driven the network, you've given us the network, we've driven the size of the video. But where are we heading after this? Well, we've got 4K. That's just about doable on some of the services today. Ultra high definition. You've also got increasing the frame rate, going from 25, 30 frames a second to 60. That's going to generate more data that needs to be shifted. We've also got people talking about 8K services now, mainly in broadcast, but they're going to come over the top eventually. But what we do see in over the top is also 360 video. Is everyone familiar with 360? So the idea there is that you transmit a spherical representation as the frame, and when you move your headset or your phone around or you use the controls, you're actually looking at a viewport that's moving around that spherical representation. So what you've actually got is you're zooming in to a specific part of the video image. So if you think about that, if your actual spherical image is being shipped at HD, what you're looking at is way, way, way less than HD, which is why often the experience looks a little bit fuzzy and a little bit poor compared with watching a non-360 video. So if we're going to do that well, we're going to have to push the source files. The actual spherical frame is going to have to be a lot bigger than HD, so it's possibly going to be pushing 8K to get a reasonable viewport. So over the last 10 years, we've been mainly using H.264 as the video compression codec. And as you've given us the bigger pipes, we've been able to get bigger resolutions down those pipes. So do we look at it and go, throughput is really a function of the pipe size? Is it a constant? Is it a linear progression? The problem is today, we typically use unicast and acknowledged delivery. So the way we send the video files today, we send them in fragments. We wait for fragments to be received before we send the next fragment. Those fragments are often sent over TCP. TCP has acknowledgements in it. So the question is, can we keep putting more throughput through the bigger pipes? Has everyone seen this before, the Mathis Formula? So this is saying that in a single stream of delivery, your overall throughput is likely to be capped by the round trip time and the error rate. And if you think about the way we deliver video today as an HTTP stream, we are effectively a single stream of video with all the acknowledgements in. So if we look at this graph, what this is showing us is the round trip time is on the x-axis, the throughput is on the y. And the limitations are based upon the error rates on the network. Red being, in this instance, a 12% loss, the blue being 0.1%. So we take the blue line, which is the best case on this, and you take a 30 millisecond round trip time, which would be considered fairly good. You're likely to be capped out at a 10 megabits data rate, sustained data rate. If you actually increase the round trip time to 100 milliseconds, which actually measuring some of the services in the UK today, pinging them from the home to their distribution points, 100 milliseconds is not unreasonable. That suggests that your maximum throughput is about 3 to 3.5 megabits. And at that speed, you can just about sustain an HD video over the top. So that's not to say that having a fatter pipe is not useful, because it is. We know that in many households now, you've got multiple people trying to stream those HD services at the same time. But on a single service, do we actually think increasing the pipe is going to allow us to increase the resolution and the frame rates that we send down it? So the first option then is we change the delivery architecture. So what if we moved away from TCP? Maybe we move to UDP. Maybe we move away from unicast to multicast. But that's going to require changes in the sort of network. That's going to require changes possibly on the home gateway. Maybe we move away from delivering via HTTP. Maybe we move to a different streaming technology. Maybe we need to move to a different caching technology. Move away from traditional CDNs, perhaps to peer-to-peer networking. And these things are all being explored today. Probably in 5 years' time, we'll look back at video delivery technology and go, a couple of those things have taken off and they are the new norm. The problem we've got is they're not ubiquitous today. So if you use those technologies, they become additive to your estate rather than replacement technology. So okay, if the bigger pipe is not the solution, do we need to look at actually reducing the bits? So how could we do that? I think that's a fair question. We could use a better codec. So today we're using H.264. Typically you're getting about 50 to 1 compression. There are newer codecs around. Has anyone heard of the likes of VP9, HEVC, AV1? They're all being touted around in the video space now. Maybe those are the answer. But there's a number of factors that you need to think about before you adopt them. The first one is the cost clear? There's a number of patent pools around on some of these codecs, and if you look at HEVC, there was an announcement this month. One of the patent pools has announced that they're not going to charge on a per content basis for electronic delivery, and they're going to set low charges on the devices. But do you know who's paying for it? Is it you, the content provider? Is it the encoding partner like us? Is it the device manufacturer who's putting this into silicon? Is it the video player provider? Probably not, because a lot of those are open source, so we know there's no money there. Or is it going to be the service provider, the application developer, the likes of Sky, the BBC? We don't know, but that's a question to be sorted out before you adopt. The second big challenge is, and certainly this is in the UK, but it probably applies equally across the globe, you've got a very large number of devices that you're streaming to. Whenever I get engagements with customers and they give me the list of devices they want to deliver to, it typically looks something like this. And that list just keeps growing. So the challenge if you adopt a new streaming protocol like H.265, which devices support it? So some devices just won't support it at all because they're a little bit old. Some devices only the latest generation. So if you want to support HEVC on Apple TV, you need a Generation 4 device. So again, if you support H.265, it becomes additive to your stack because you're less likely to abandon all of your existing users with devices that are only, 3, 4, 5 years old. I mean, hands up here who's donated their iPad to the kids and the kids use it for streaming. You know, Are you going to want to spend £400 buying the kids a new iPad so that they can continue watching the services that they consume? Probably not. So if today we're not going to just wholesale shift to a new delivery technology or to a new video codec, can we do something to optimize the use of H.264 further? So Brightcove is, as one of the leading OVPs, we are still looking at H.265. We've got it supported in our platform today. And we are looking at the next generation technologies. We're working with our partners in the ecosystem on that. But over the last couple of years, we've put some of our R&D money into optimizing H.264 and actually using machine learning to optimize the use of the codec. So our premise is, if we can optimize it and you can keep using those devices for another few years, again, we push off this problem of when do we make a wholesale change. So if we look at a video publishing architecture, a typical architecture, you can see on the left that you acquire the content from a mezzanine encoder or potentially a mezzanine file from post-production. You go through a process of ingesting it, which is acquiring it into your platform. Then you have to demux it, which is stripping it back to the elementary audio and video streams, potentially some metadata. This then gets encoded. The encoding process is our lossy process, where we reduce the size of the file. And we often produce a number of resolutions and bit rates from that, and I'll talk about that on the next slide. Once we've compressed it, we then package it back up into a supported file format, so ISO-based media file format or transport stream. We also put that into a container that describes all of the different resolutions that we have with a manifest file, which we then deliver to the devices through a content delivery network or some other caching tier. The players then consume the asset, and typically you'll see that players have beacons in them which fire back metrics and statistics. So it's not only just on what you're watching, but also the quality level and the bit rate and the buffering experience that you're observing. So the next slide talks about the single bit rate versus adaptive bit rate delivery technology. In the old days, sounds old, but it was probably like about 10 years ago, we used to take our video and we used to encode it into a single bit rate. So if you had a 50 megabits per second high quality broadcast source, you couldn't ship that over the network, so you reduced it down to maybe 1 megabits per second. Now the problem with that is, if your network can't sustain a throughput of 1 megabits per second, you're ultimately going to buffer, and the user is going to get that pausing and the spinning wheel kind of logo while the video catches up, while the network catches up. So what we did about 10 years ago was a number of protocols came out, or a number of container technologies like smooth streaming and HLS, that said, let's produce a number of quality levels at different bit rates that are chunked into either 2, 6, or 10-second durations, and they're all aligned. And we'll tell the device these are all available, and the device can choose what it can play best at any given time as the network throughput fluctuates. So they're all synchronized so that as you switch between them, the video doesn't jar, the audio doesn't jar, but you'll see the quality go up and down. And I suspect everyone in the room has experienced that when they've been watching some of the services that you use. And this is still the technology that is mainstream in use today. Even though we've got newer versions of container technology like MPEG-Dash, it's still using the same fundamental capability. So why do we think this is inefficient, or why have we proven it to be inefficient? And it's really down to the fact that not all content is equal. If you think about the amount of information in a frame or a series of frames of fast action movie or fast action sports, compared with the amount of information that needs to be shipped in a talking head, a cookery show, or potentially an older kids animation, one that hasn't got all the great shading and graphics and things that they have now. But if you talk about those, they've got a lot less data in them needed to portray the same quality when you compress it. So the premise here is that it's easier to compress some of this content than others whilst maintaining the same quality. So the inefficiency comes from the way people choose their what we call the bitrate ladder. so these different quality levels that they're going to encode the content to. Most people will take a standard and start with that. They'll take Apple's guidelines for HLS, maybe they'll take the Video Cloud, our products, standard guidelines. And so this is the bitrate ladders going from, say, 450 kilobits up to 3.8 megabits. And they will pick that and they'll apply that to all of their content. And this is where the inefficiency comes. So let's look at some of the science behind it, some of the maths. So if you make an assumption that for a given bit rate you can achieve a certain quality, and if you plot those points on a graph as a sort of normally monotonic function, you'll find that you've got a bit rate minimum and a quality level minimum, at which point the picture is just so useless. You can't go below it. So we call that the rate minimum or the quality minimum. You'll then find that as you reach saturation point, increasing the available bandwidth doesn't actually, or increasing the bit rate, doesn't actually noticeably increase the picture quality. So you've got a sort of a point where you're saturated. And so for any given piece of content, you can actually plot that graph. And you can work out what the quality min is and the quality max is. And it will be different for different pieces of content. The other challenge that we have is the standard measures available for quality, so things like MSE, the signal-to-noise ratio, SSIM, FSIM, all work by comparing the codec level noise on the same size image. And of course, with the adaptive bitrate technology, we've got different resolutions as we go up the ladder. So they're not perfect, but they're pretty useful. But what we're not doing is looking at actually the experience on the network. So if you look at this diagram, the one on the left is talking about that S-shaped curve. So what we've done here is mapped a number of different types of content and given you those different quality function curves. So you can see some content, you can use a far lower bit rate and get very high quality. So that's the blue lines at the top. And this pink line that's drifting over here is one that's obviously really, really hard to compress whilst maintaining quality. And this is often what's referred to as content-aware encoding, or sometimes per-title encoding. So that says, analyze the content in isolation, and then you can basically choose the compression settings for it. What we've done with machine learning, though, is taken in all the real data coming off the network, off the players that's been beaconed back, that's saying, what experience are people getting? What bit rates are they typically consuming? Okay, and we're then using that to drive the decisioning of which profile gets applied. And the reason this is used machine learning is because we're basically continually gathering this data and comparing it with the source files and working out what those quality maps are. So if we go back to the architecture, what we can see here is we've built in this profile generator into the architecture. So that's taking in the content itself, which is the left arrow coming in. So that's where we're analysing the content's complexity. We're determining what that graph looks like for the quality rate function. But we're also taking in the data from the network, from the players, about what the network experience is, because the network is always changing. It's always improving. Latencies are coming down. Effective throughputs are going up. And then we're able to process all of that and choose and tune the optimum set of encoded outputs that we're going to use. So this kind of tries to explain it perhaps a different way. So we've got the S-curve on the left, the quality rate function. On the right, we've got the probability density function, which is what bit rate are we likely to be getting on the network? Or where are the peaks of the bit rates that we get? Because there's no point in having a step jump that doesn't align with the likelihood of that being achieved on the network. So if we take the graph in the middle, if you were somewhere between those two points where the blue line joins the red line, then you're saying, I'm not able to step up to the next quality level because I'm unlikely to do that on my network, but I'm also way above this quality level, so I'm actually sacrificing some potential quality that I could get. What we've also done is looked at it and said, well, if you had 8 quality levels today on a piece of content, and then you shift that graph massively left because you understand that it's a different shaped graph, would you still need 8 step points? Is that efficient? So ultimately, through the machine learning, we've been able to optimize that bitrate ladder. So we can not only say what is the best maximum bit rate that we should be using to get the, if it's HD, to get HD, but we can also look at optimizing the step jumps on that curve to make sure that as the network conditions fluctuate or you switch between broadband and cellular networks, we've got a bit rate that is optimized for the high probability of you actually getting that network throughput. And so what we've come up with is, through the machine learning, is a set of optimal ladders that we can then select and apply based on analysing your content. So the content that's easy might only have 4 bit rates, and it might peak out at, apologies, it's very small font, but it peaks out at just over a megabit as the maximum bit rate. You've got really complex content, and that's got 6 bit rates in the ladder, and it peaks out at 3.5 megabits. Okay, so we're taking the complexity of the content and mapping on the probability of you being on a particular throughput on the network using machine learning and generating the optimization. So the way we've kind of positioned this in the way we kind of take it to the market is to say it's the compression expert in the box. So the machine learning is our science that's under the hood. We've got patents out on some of that stuff, and if you look at the research papers on it, it blows your mind, some of the formulas that are in there. I stripped them off the presentation because I didn't want to absolutely bamboozle everyone. But the idea here is, the premise is, we can potentially reduce the amount of data that's transferring over the network by 50% whilst achieving the same quality level, which for everyone here that's trying to size the networks is probably a good thing. So I'm going to see if we can play this video to show you. So what I want to show you here is actually 2 videos playing that I've got a very similar quality level. I think you would be hard-pressed to distinguish between them. So what you can now see here is the one on the left is the traditional encoding technology, and it's playing at it's using 2 megabits at 720p, and the one on the right is still 720p, but it's only using 1.3 megabits. And trust me, if you had them side by side on 2 very large screens, you wouldn't tell the difference between them. So to zoom in on that, we've got another video here which we've grabbed some stills from. The one on the left was consuming just under a megabit. The one on the right, with the new technology, with the machine learning applied to it, is only consuming just over 680 kilobits. What's interesting to note, though, is the way the ladder has been optimized. The one on the right is actually a higher resolution as well. So we've picked a higher resolution, 960 by 540 instead of 640 by 360. And yet we've got a 31% smaller file size. Just to zoom in on that, anyone who's watched very compressed videos will know that it's often straight lines that are not perpendicular where you see the compression artifacts and the noise. So just to highlight this, that railing is definitely sharper with the one on the right than the one on the left. So machine learning is able to give us a higher quality with a smaller file size. So in summary, applying machine learning to the encoding problem, it allows the service providers, the content providers, to do one of 2 things. They can either stick with their existing target quality level, so for instance 720p, and instead of generating a bitrate ladder with maybe 8 steps and a top bitrate of 2.5 megabits, they can actually shrink that down, maybe only have 5 renditions, and have a bitrate at the top end that is, say, 1.5 megabits. So there's 3 benefits actually really to the content provider. The first is if they pay for the processing power for transcoding, which is quite typical. Services like us, we charge for the minute of encoding across all the bit rates, but if you have to buy your own hardware, you've got to size the hardware to cope with what you're doing. So if you're producing less bit rates, it's going to be cheaper. If you're producing less bit rates, you have less to store, because all this video on demand content, once it's processed, has to be stored on spinning disk somewhere to be able to be delivered to the network when it's required. Further, because you've got a smaller top end bit rate, your largest set of encodes is also going to be smaller. So you've got a double whammy on reducing storage. The real big benefit, though, if you're a large-scale provider, is in the fees that you have to pay to deliver that content. So caching technology, the CDNs, the Akamais, the Limelights, the Level 3s of the world, they charge per megabit, gigabit, terabit that's shipped through their caching network. So if your user at 720 is only pulling 1.5 meg instead of 2.5, you've potentially got a huge bandwidth saving. It's also good for the people who own and run the networks because they need to ship less through it. The other way of looking at the problem, though, is if we go back to the original, is resolution and throughput going to be a factor of the pipe size? Resolutions keep going up. We want to go up to 4K. We want to go up to 8K. Maybe using this technology allows services to get more down the current pipes. And so instead of capping out at a usable 720p, maybe they can deliver 4K or UHD over the same quality of network and maintain a good customer experience. So it's kind of a choice on how people use it, save money or do more for the same cost. So that's machine learning applied to the compression space, which I think you agree is pretty exciting. We can stretch out H.264 for the next few years whilst the hardware and the network topologies ultimately roll out to the masses. But where else are we seeing machine learning being used in the video space? So the first one is highlight clipping. Being able to analyse, say, a sports game, 90-minute football match, and you want to produce a 10-minute highlights package. Can we use machines to actually understand the semantics of the video and the audio? Who here has the habit of being in the living room with the television on, but they're on their iPad or their work computer checking emails? Everyone do it? And how many times do you subconsciously look up to the television because you've heard the audio change, something's happened, and you go, oh, what's going on? Was that a goal? Was that something or other on the game? We all do it, and so you think, well, actually, we could train machines to do the same thing. You've got a football game, there's a big cheer followed by, oh, maybe there was a missed goal. That's potentially a highlight clip that you want to take. There's a big cheer, followed by, actually, in the center of the image, there's now a circle. We've gone back to a restart, a kickoff. You can kind of link the two together and go, okay, that's telling us what must have gone on in the game. Why might this be important? Well, we're starting to see people move away from the concept of channels. Why have 10 Premier League games on and only 2 broadcast channels that you have to put them down? And then you have to go this inconvenient thing to all the supporters of moving the football games around so that they can fit the TV schedule. Yeah? Anyone else go to football and get annoyed by the games moving? So what if actually you can just spin up channels online? Don't need a channel, you just spin up a stream. And with OTT you can do that. So it's likely we could move back to Saturday 3 p.m, all the football games are on. And you pick the game that you want to watch because they're all on an online service. Well, then at the end of that game, you're going to want to look at the highlights of all the others, and you're going to want it quick. So, we want this highlight packaging turned around quickly. Maybe there's an opportunity there. The next one is ad breaks. Sometimes you get content and it doesn't tell you in the metadata where is an appropriate point to put a mid-roll ad. Again, we could apply machine learning, look at the frames, look at the scenes, look at the audio, and work out where would be an appropriate point to insert ads. We could also do it where we analyse what's in the content. Actually, we've got a piece of content here that's got a lot of cars in it. We know there's Jaguars, there's some Mercedes, there's something else. Maybe we can use that with the ad sales team to say this content might be suitable for this type of ad placement. Okay, so rather than having to have people define all that metadata, we can use the machines to do it. The other one is captioning, subtitling, especially if we can get the power to do this live real time. That's always a thorny problem for broadcasters, especially with the accessibility rules that we have. Being able to apply captions to a significant portion of your content is a requirement. Anything where machines can take the audio and the semantics of the video to improve the accuracy has to be a good thing. We all know at the moment if you just listen to audio and try and type it, you sometimes get it wrong. And sometimes it goes wrong quite badly if you ever watch some of those services. And then finally, one that I'm quite interested in is the idea that we could use machines to actually do the editorial, the director role. Could you have things like a sports game again with a couple of fixed cameras, a tracking camera, and actually have machines work out what shots to actually take and not have somebody sitting in a gallery doing it? Could we actually automate some of that process? That's really my food for thought on that. That's the end of the presentation. I'm happy to take questions. I'm also happy if you guys and ladies have seen any ideas of where you think machine learning could be applied in sort of the video space. Happy to take questions.
Thank you very much. Very interesting presentation. A couple of questions, if I may. First of all, I'm presuming this is targeted at VOD mostly. Do you see any applications to live content? How might it be extended to facilitate that?
Yeah, I mean, we've deployed this into the VOD space. It does slow down the encoding process because we have to analyze the content and then map it to the right ladder. I guess as processing power increases, then I don't see why with live you couldn't do it. The other question with live that you could always do is you could delay live potentially. Does live always have to be live? I think the challenge with live though is you can't analyze all the content because it's not there. So perhaps live might be a heuristics thing. Maybe live you go, well, what type of content are we broadcasting? It's going to be a football game. Right, well, our machine learning off previous archives of football says this is probably what you should do. It's a chat show, it's a parliamentary debate show, it's a cookery program. Maybe we can apply the machine learning to optimize that way. But yeah, I think live is a lot harder to do.